This is going on page 100 when we're done. We looked at surface area of pyramids yesterday. We're going to look at cones today. So our first definition is the definition of a cone. Right? So a cone is a three-dimensional figure with a circular base. The base always has to be a circle. Can't be anything else, or it's not a cone. And a curved lateral surface that connects the base to a point called, and I left off the line here, but what's that point called? The vertex. And it is the vertex. It's the one and only in a cone. The vertex. Okay. So the vertex of a cone is the point opposite to the base of the cone. Is it the only point on the cone? Careful. How many points are on a cone? An infinite amount. It's the only vertex. It's the only pointy part. If you want to talk about it as a pointy part, you know, right? Technically, it's not the only point because there's an infinite amount of, but it's the only vertex that exists, and it doesn't exist in the same way that other vertices do because it's not where the edges meet. So, all right. So then the next thing is blank of a cone is the segment with its endpoints at the vertex and the center of the base. Okay, so on the pictures down here, it would be like the red dotted lines. Okay, the altitude or the height, what do y'all think about that? What's missing for either one of those to be the right answer? Okay, segment for it to be the altitude, and, well, it does say segment, so it could be the altitude, but what would be missing for us to say we know that has to be the altitude? Perpendicular, exactly. So both of these cones are right cones. So that segment that I'm trying to fill in the word for and altitude happen to be the same segment, okay? But because it doesn't say perpendicular, if this was an oblique cone and it's leaning over, it would still be the segment that connects the vertex to the center. And we had these in a cylinder. What do you think it is? What connected the centers of the bases in a cylinder, whether it was a right cylinder or an oblique cylinder? Look at your notes if you don't know. So what? What connects the center of the bases of a cylinder? The axis, right? The axis is what it would turn around. So this is the axis. If the axis is perpendicular, then it is also the altitude, right? But it doesn't have to always be the altitude, just like in a cylinder. If it was an oblique one, it's still the axis, okay? And then if the axis is perpendicular to the base, then what kind of cone is it? I've said the words. A right cone. So a right cone. And then cone whose axis is not perpendicular to the base, which would be what? What the leaning one's called? Oblique. Good. An oblique cone. All right, everybody okay with that? All right. Now let's look down here. So the blank of a right cone, okay, so we're only looking at right cones right now, is the distance from the vertex of the right cone to a point on the edge of the base. So it's my blue dotted line here. What do you think that might be? Slant height. Okay, so in a pyramid, the slant height had kind of the same definition, but it went to the center, or into the midpoint of one of the lateral faces, or the base of one of the lateral faces, and it was the height of one of those triangles. Well, there's not actually any triangles here because it's a smooth surface all the way around, right? But it is still the distance from the vertex down to any point on the edge of the base, okay, on the edge of the circle, because it would be the same all the way around. All right, so this is the slant height. And what letter do we use to represent slant height? L. Good. So this is the slant height. And it's an L. So then what is this red dotted line? It is the axis. It is also the what? Altitude, which means the length of that is the height. So we label it with H. When I connect these to get that triangle floating inside like we did for the pyramid, what is this segment here? Is there an apothem of a circle? Yeah, no, it's the radius. Everybody okay with that? All right, so the blank of a cone is the segment from the vertex to the plane of the base that is perpendicular to the plane of the base. So when we say it that way, what is this? Altitude. Good. So this is the altitude. Those little, like one little word can completely change what you're trying to say here. So this is the altitude, which we represent with the height, right? This, what is this? The radius. Okay, so this, then, the way this one's drawn, that segment, which isn't really a segment, it isn't really an edge, it just looks like it two-dimensionally. What does that represent? The slant height. Okay, so if I'm given the height and I need the slant height or the radius or vice versa, I've got a right triangle there, again, where I can use it to do what I need to do. Okay, we good on that? All right, so we're going to pause right here. You need to have your nets out from yesterday, and I'm going to give you one more thing. Be very careful not to tear its head off. These, to me, look like if you were on social media and you don't have a profile picture, like this is what you look like. Right? Okay. Alrighty, so here's what we have. I'm going to go ahead and glue mine down. Remember, glue it down so it's not hanging off the paper. It should fit just fine. So then when you take this, if you build your cone, now because I didn't make these nets where you could actually like glue them or tape them closed purposefully, because then you have to have flaps and extra pieces and stuff, and I wanted it to just be the figure itself. So when you build this, okay, in order for it to stay, and it does work right, you kind of have to cheat a tiny little bit. And right here where the vertex of the cone would be, if you just pinch it a tiny little bit, just at the very top, then it'll stay a little bit better when you're trying to hold it. Does that make sense? Otherwise it kind of, and it does fit correctly and perfectly. I promise you the measurements are right. Now when they were cut, it may have been cut just a little bit, you know, off or whatever, but if you did have like 4 hands and you could hold this together well, it would make a cone. So I just want you to see where the pieces come together and how all this stuff works and how you get a cone from it. Okay? I know. You kind of have to have extra hands and the paper is not that cooperative, but you get the idea, and that's what I really wanted here. Because for a cylinder, I think there were some of you that hadn't seen a net for a cylinder, but most people had. How many of you have never really seen a net for a cone? Okay, right? Without doing it, you might have looked at that and been like, what the heck is that, right? But now that you put it together, do you see how that works? Okay. No? No? Okay. Help him out over there. Build his cone for him. Okay, so do you see how and why it looks like this? Okay. So for our cone, we've got a couple pieces here. We've got the circle, which represents the what? The base. Let me see if I can turn the light on here. I don't know if that helps any. Can't really. It's the purple that this doesn't like very much. Okay. So this is big B. And then since this is a circle, big B is always what? Pi r squared. Okay. And we are interested in the radius. That's what helps us get what we need to get there. Okay. Now, look at this part right here. The lateral surface for a cylinder ended up being a rectangle, right? It ended up being a figure that we already knew. The lateral surface for a cone, what is this? It's a portion of a circle. What do we call a portion of a circle? A sector. Do you see how the base is a circle? The lateral surface is just a sector of a different circle. Does that make sense to you? Okay, so use your ID for a straight edge. Just plop it up there on... And I want you to draw in the radius, and it doesn't matter where, because it could be anywhere, but I want you to draw from, because this would be like the center of that circle, and I want you to draw the radius of this sector in. Like so. Okay. And so although that line, which I know is hard to see on my paper, but that line is the radius of that sector of that bigger circle, What part of the cone is that line segment we just drew in? It is the slant height. Okay? So that you can see it better, I want you to do the same thing by just like flip this over and flat so that you can draw on it, because if it's not flat, you can't draw on it. And then draw the radius on the outside as well. And that is the slant height. If you don't believe me or that doesn't make sense, then build your cone and you can see how that works. And it doesn't matter where I drew it, it would be the slant height. See that O there? That's why we're doing this, even though it may seem silly on some of them. Because until you actually physically do it, it doesn't always make sense to everybody. All right? And I could have drawn it over here if it really is still kind of weird to you, draw another one. Because the slant height can be drawn anywhere on the cone. I can draw this anywhere. That's still the slant height. And when I build it up, it still goes from that vertex to any point there on the circle. And it's the same distance because it's a radius of a different circle, and the radius is the same all the way around. Does that make sense to you? Okay. Do you know how to find areas of sectors? Yes. Then you can find the lateral area pretty easily. We're actually going to do it a little bit differently, but it's still the same type of thing here. Okay. Then this point right here, which is the center, which is the center of the circle that this sector comes from, what point of the cone is that? The vertex, yes. So we're going to label that. This is the vertex. So we could come up with the lateral area and surface area formulas using the idea of a sector, and that can get us there, all right? But we can look at it a little differently as well. Just like with prisms and cylinders, pyramids and cones are very similar to each other. They also are very different. I mean, they have a lot of different properties, but they are pretty much the same. So just like with the cylinder, I told you, if you don't remember the cylinder formula for lateral area, if all you know is what it is for the prism, you're fine, and it works, right? We just, we kind of call things differently, but we know what it means and we can make sense of it. Same thing goes for for pyramids and cones. In the end, they're going to look a whole lot more different than prisms and cylinders did, but still, it's the same thing. So what is the lateral area formula for a pyramid? What is it for a pyramid? Good. Lateral area is 1/2 perimeter times slant height. We came up with that yesterday from our triangles, and it all made sense, right? Well, we don't have any triangles here. But this exact same formula works here. But the difference is, just like with cylinders, we don't call it perimeter. What do we call it? Circumference. And then we know that circumference is always, what's the formula? 2 pi r. So to make this more circle-like, I'm going to substitute in the circumference formula for the perimeter. And that's going to give me 1/2 times 2 pi r times the slant height. Can I simplify this any? Yeah, what's 1/2 times 2? 1, right? So I don't really have to multiply by 2 and then take 1/2 because they're just going to cancel each other out. So the lateral area then for a cone is just pi r L. So it looks differently because it's like it's missing the 1/2, but it's not really missing the 1/2. We used it, it just got simplified out of it. All right, does that make sense to you? And this is easier than using the whole sector idea, although you need to have that concept in your mind because there might be times where you need to find that or have that for some reason and understand how a sector of one circle could be related to a circle of another to get you a cone, right? The original net that I got this from, like this was from an activity that I was shown like many years ago and I've adapted it a bazillion different times, but the lateral surface was a semicircle, which is a possibility. But then it made everybody think that the lateral surface of a cone was always a semicircle, and it's not. It can be less than a semicircle, it can be a semicircle, it can be greater than a semicircle. So I want you to think about this. The bigger that this sector gets, so if this was to become a semicircle and then more than a semicircle and you get closer and closer to being a circle, how would that affect what my cone looks like? What would happen to it if this, so you have this cone, right, with whatever the dimensions are. If we made this sector here more than a semicircle, how would your new cone look different than this cone? Okay, well the base is going to stay the same. Okay, so it's going to get shorter, right? It's going to get shorter and fatter because this is going to have to actually get a little bit smaller. Well, yeah, okay, I see what you're saying. The circumference of the base would have to be, yes, you're right. You can do it one of two ways. You can kind of leave this the same and change how much of the circle, which would change this radius here, which would then change that circumference. Or we could leave this the same size sector, which would change the size of the base. And then as that base gets bigger, your cone gets shorter and fatter, right? The taller and skinnier it is, the less of this sector you have. The more of this sector you have, the shorter and fatter your cone is. Does that make sense? You can kind of like visualize that a little bit. Okay. We all good so far? All right, so let's look at lateral area for our cones here. We actually have a couple of options. Lateral area, we can think of it exactly the same as this, 1/2 perimeter times slant height. It's the same thing. You will never see it on a formula chart like that, because on a formula chart, they're never going to talk about it as perimeter, because it's not really what it is. But it works. So if it's the only one you know for pyramids and cones, it works. And you can just substitute your stuff in and go with it. But what that actually becomes, and the one you really want to use, is lateral area is just pi RL. So then for total surface area, you can use this one right here. I mean, this one works for sure. But I could say, all right, let's say I already know the lateral area, so I'm just going to substitute that in. Then the base, I don't have to use big B because it's always a what? Circle. So it's always pi r squared. And there's only one circle. For a cylinder, we had 2 pi r squared because there was 2 circles. Or if I'm doing it from scratch, then it would be pi RL plus pi r squared. But again, this one, and I think this one right here is just the basic concept, and you can go and take the stuff and substitute it in. So whichever one makes the most sense, or at whatever point you are, then you're good. All right. Any questions at this point? Good. Did you learn something today so far? Good job. All right. Let's move on. So now we're here. And this is a right cone. We've just, which means this one is an oblique cone. We don't have regular and irregular because you can't have a regular polygon as the base because there are no polygons here. These are pointing to the vertex. This blue dotted line is the slant height. And yes, I know we've written that over and over and over again, but I'm hoping that that means that we won't ever mess it up. That's right. So this is, and I know sometimes it's hard to tell what these are even pointing to. This is pointing to the lateral surface. What are the red dotted lines? Axis, good. And so I think I'm going to extend those a little bit so that I can only write it once. And then these are the bases. Okay. Everybody good? No? Okay. Oh, on the line here. Yeah. Well, and that's okay, as long as you can, so, I mean, because that's fine. They just make the vertex, and it'll work. All right, so now here, lateral and surface area of a right cone. So this only works for right cones, and we just came up with it, so we're just going to rewrite what we have with our nets. Lateral area is 1/2 perimeter times slant height, but that's kind of cheating, but it does work. What we really use as lateral area is pi r L. Surface area, you could do lateral area plus big B. That's just the basic overarching concept. Or lateral area plus pi r squared. Or pi RL plus pi r squared. These two are really the ones that you would most likely see on a formula chart of some sort. This here could represent my height. This is my slant height for the cone itself. When you make a net out of it. You see the bigger circle that this sector comes from? The radius of this circle is the slant height. And just like with the radius, you could draw it anywhere around the circle, and it's the same length. Now this, and I forgot to say this on the cone. Let's go back to our cone real quick and just kind of look at mine. The circumference of the base is what part of this circle? The arc. So this arc length, whatever the arc length is, not the measure, but the distance, the arc length is the same as the circumference of the circle because that's what wraps around that circle. Does that make sense to you? Okay, good. So this part right here, that arc length equals the circumference of the base. Okay, so the arc length equals the circumference of the base, because that's what wraps around. Just like the side length of the rectangle was the circumference of the base for a cylinder. Okay. We're all good with that? Yes. All right. So now we're going to find the lateral area and surface area of the cone and give our answer in terms of pi, which means we do not need a calculator. So I start with the lateral area. It is pi RL. Okay, did they give me the radius? Yes, it is 5 feet, so I don't have to worry about messing up with diameter or anything. Did they give me the slant height? No. Can I find it? Yes. This is the slant height that I need. What do I do to find it? Pythagorean theorem. So it's 5 squared plus 12 squared equals L squared. 25 plus 144. L squared. L squared is 169. So what is L? 13. Okay. So this actually is a Pythagorean triple. You didn't recognize it? That's fine, because you know what? When they're Pythagorean triples, it makes Pythagorean theorem really easy. No big deal. So L is 13. So now I have everything I need to substitute back in. I get pi times R, which is 5, times L, which is 13. What's 5 times 13? 65. So the lateral area is 65 pi feet squared. And you never leave pi first, okay? Pi comes last. It comes first in the formula because it's a number and then you have variables. It's because your variables come last, but when you write it like this, it's 65 pi. It's not pi 65, okay? We're good? All right, so then I need to find the total surface area. Well, since I already have the lateral area, I'll use lateral area plus pi r squared. So that's going to give me 65 pi plus, I already have the radius, that's good, pi times 5 squared. What's 5 squared? 25. So I end up with 65 pi, oh, okay, fine. 65 pi plus 25 pi. So my surface area is 90 pi feet squared. Everybody okay with that? Any questions at all? All right. Let's look at the next one. It says, find the lateral area and surface area of a right cone with a diameter of 12 meters and a height of 3 meters. Give your answer in terms of pi. So I'm going to give you a minute while I go check roll, right on cue, to draw and label this and find this answer, and then we'll talk through it together. I saw this meme last night that said, every teacher ever before writing on the board. Okay, so I'm not an artist, right? I am not an artist, but we're going to do the best we can here. All right, so when you go to draw a cone, the base is a circle. Do you really draw a circle? No, you draw an oval, right? Because it's like on the two-dimensional space. And then it helps the visualization if the back part of the oval is dotted. If you need to draw it and then go back and erase to make it dotted, that's what I do sometimes on the harder figures, but kind of goes like that, and then you can just attach them like that. Close enough. It's okay if it's not dotted, but sometimes it throws you off, right? So it says, blah, blah, blah. The diameter is 12. And the height is 3, and I want to find the lateral area and surface area. So my lateral area is pi r L, right? And did they give me the radius? No, they gave me the diameter. What is the radius? 6. So I want to make sure I use the right thing. Did they give me the slant height? No. Okay, so that's 3, that's 6. I got to find the slant height. So is that a special right triangle? No. Or a Pythagorean triple? No. So 3 squared plus 6 squared equals L squared. 9 plus 36 equals L squared. L squared equals 45. Oh, I just wrote 44. So what is L then? 3 squared of 5. Very good. Okay, so 3 squared of 5. So come back over here. Pi times 6 times 3 squared of 5. Lateral area is what? 18 squared of 5 pi. And what is it? Meters squared? And be careful when you are doing those things that your pi doesn't look like it's under your square root sign, right? So surface area is lateral area plus pi r squared. So that's 18 square root of 5 pi plus pi times 6 squared. 18 square root of 5 pi plus 36 pi. Can I combine those? No. So that's my total surface area, parentheses, meters squared. Okay. Any questions? Yes, sir. Okay, that's a good question. The question was, if I'm going to enter this in Schoology, which number goes first? It does not matter. Okay, so when in there, I put both choices. Okay, that way it'll take it. Now, if we have like 3 or 4 terms, I may tell you to do a certain thing because then I have a ton more I have to type in. But I type it in both ways. Just make sure your pi's are last. Okay, does that make sense? It's a good question. All right, anything else? All right, so then I want you to look at the next one. I want you to write down a plan. Actually, I want you to write down 2 different plans. Okay, you would only have to use one. But I want you to write down 2 different plans while I hand out the homework, and then we'll talk about what they are. By now, hopefully this is getting a little bit easier for you. My disclaimer on that Schoology thing is that I'm not perfect, and I know it's painfully obvious that I'm not perfect. So there is a chance I might mess those things up every now and then, but I try really hard not to. Somebody usually catches my mistake pretty quickly. All right, so there are actually 4 different plans that could work here. Somebody give me one. Who wants to give me one? What you got? All right, so what do y'all think about that? Surface area of the cone plus the lateral area of the cylinder. Is that right? Does that work, brother? Yes, because my cylinder, here's my cylinder, right? And there's just the lateral area. Here's my cone with the surface area. When I put it on there, I got 2 problems. This has a circle and this doesn't, but can you see how that would just like fall to the bottom and take care of it? Okay, so that works. May not be the favorite for some people, but it totally works. Okay, somebody give me something different. What you got? Okay, and then that's it. Okay. Here's the surface area of my cylinder. Here's the lateral area of my cone. Do I have a problem? What do I need to do now to make this right? Subtract the circle. Does that make sense? Do you see why I have to subtract one? Okay, good. Somebody give me something else. Good. Surface area of cone plus surface area of cylinder minus 2 circles. So that's the all-together idea, that if you struggle with this, find everything. Put it together, think about what you don't need, and you don't have to worry about things moving around or whatever else, okay? What if I found the lateral area of the cone plus the lateral area of the cylinder. Then what? I'd have to add a circle. Okay. Now, do you have to fully comprehend all of those and be able to come up with all of them? No. Do you have to use all of them? No. Do you have to, at the very least, understand one of them? Yes. But I want you to see that there's different ways. Everybody at your table could do it differently. There's no reason to argue about it. Hopefully they make sense if somebody explains them to you. You may not have thought of it, but that's okay. All right. Any questions here? We good? All right. So go ahead and get that glued in. I passed out the homework, right? Awesome.